Okay, to tonight's talk. Like a lot of our talks, they've been in gestation for some time, so I've built up quite a lot of anticipation to hear the speaker tonight. He's very involved in the subject. I think he seems to eat, sleep and breathe the subject, since he has so many roles, both inside and outside Oxford University. So he's going to be talking about driving autonomy and artificial intelligence and robotics. So I'd just like to introduce Ingmar Posner, who's going to speak to us about robotics. Thank you very much.
Oh, thank you. All right, so hello everybody. Thank you very much for coming. It's a real pleasure to be here. The room is probably small enough that we can make this so I don't talk at you. Okay, so we can make this a bit of an interaction, right? And so please feel free to just interrupt, shout out, and we can have a bit of a conversation. I have like a billion slides. I can talk for a long time. If I only show you one and instead we have a good conversation, that would be kind of fun. Okay? Let's even try that. All right. For those of you who have seen parts of this talk before, if you went to Geek Night about this, you might have seen some of this before. Apologies. But I'll find it interesting anyway. All right. So the idea is that for the next 45 minutes or so, I would like to tell you a little bit about what we do at Oxbotica. And one of the things that we do there is sort of autonomous driving, but I will tell you about how what we do is sort of much broader than that. It's actually about mobile autonomy, and we'll get to that. And so what I will propose is that I will tell you a little bit about sort of our ambition. I'll tell you a little bit about our philosophy, our thinking, how we approach stuff, and how we approach the technology. And then I'm going to talk in a bit more detail about the actual technology. Does that sound like a plan? Yeah? Okay, wonderful. All right, let's start with that. So, this being Oxford, and this being Oxbotica, we were never short of ambition. Our vision for this really is that we will develop software that will drive all vehicles everywhere to deliver true autonomy, etc., for people and for goods. Okay. Now, that last bit, this bit here, is actually really, really quite important. And I mentioned a second ago that we can talk about autonomous driving, which of course everybody's sort of very aware of right now. It's a very hyped sort of topic. And most people think about autonomous driving in the context of cars that typically don't have steering wheels, probably don't have windows, but they do have a couch, they do have a microwave, right? That sort of stuff. We're not really in that place, though we do do autonomous driving on road. I'll talk about that. But there is so much more out there. There's so much more out there that is both interesting, immediately useful, and also a lot sort of less on the radar of everybody. So for example, if you ever ordered anything from Amazon, chances are that went through a completely autonomous port terminal. Okay? And how they do autonomy there is an interesting thing because it's somewhat narrow, it's somewhat cumbersome is probably the best word I can think of right now. We can talk about how our technology fits into that. I want that. I want that market. I don't just want the $1 trillion that we talk about when we talk about on-road driving, but I would like to operate in ports. I would like to operate in airports because it turns out that a lot of damage is done by vehicles on the air side crashing into planes. And we've done some stuff. I'll talk about that. And it's an interesting conversation that you have when you talk to an insurer about doing autonomy next to a 787. Okay, the price tags change in an interesting way. So there is that. There is mining, right? There's a whole bunch of mining that's out there with open cast, closed cast mines, where there is a lot of money being spent in automation, both for safety but also for efficiency. Right? That's a big bit. So all of logistics, there's last mile delivery, etc. When I say that Oxbotica is a mobile autonomy company, that is what I mean. We want to reach into all of these places, not just on-road driving. Okay. Now that is interesting for one very big reason. Because we want to reach into all these domains, I don't want to have 16 development teams typing furiously because it doesn't scale well, right? Ideally, I'd like to develop one technology stack that deals with all of those things. And that is what makes us really, really, really different from basically everybody else out there. And that's sort of what I will talk about, and I'll talk a little bit about how that technology comes together. Okay? All right, so that's our vision. I hope you'll find it sort of to your taste. I hope you'll find it's sort of ambitious enough for us. Just shy of world domination. I also have a real privilege here because I'm delighted to be able to stand here and say we're one of the very few companies who've actually done stuff. Okay, so this is now a few years ago. This was in Milton Keynes. That was sort of probably when we started again, so I can kind of give you a running commentary of that. So this was in Milton Keynes, where we did a thing called the LUTS project with the council there, and that was, as you will notice, not on road. This was sort of in the pedestrianised domains, but it was in and amongst the public. That's super, super important, right? This is not closed off stuff. This is the same sort of thing, different form factor. Different form factor vehicle around the Old Arena in London. This is Summertown, so this is our vehicles going around Oxford, where we sort of do very, very high frequency deployments right now. We talk about insurance in the loop, we talk about the full perception stack, and I'll tell you something about how that works later. Important to us is we don't use any GPS, we don't actually use any INS, but we're what we call infrastructure free. So we don't actually rely on having any third party outside sort of information coming in, right, other than what we do onboard sensing. And we operate in different environmental conditions. More on that later. We're the first people to operate airside at Heathrow. If I switch the sound on, you'll hear our guys go plane, because aircraft are so much more exciting than autonomy. We operate in ports, so this is actually the port of Singapore, and the interesting thing about that is that we managed to get a guy on the plane, off the plane, and deploy within about 30 minutes of getting there. This is autonomous grocery delivery with Ocado. There was a trial running for a few weeks last year. This is the guy, first ever person to have their cabbages delivered by an autonomous vehicle. Super exciting. We operate on-road, we operate off-road. That's also very, very important for a number of reasons. Particularly, think of that not as bush, but think of that as unstructured environment, highly unstructured environment. Mining I've already talked about, and there's an interesting thing here. If you look at this, you see those tread marks, those tire marks? You'll find that the vehicle actually runs in those tire marks. And that's interesting because those are our own tire marks from going around that mine a lot. Okay? So our localization is accurate enough such that we can follow our own tracks, right? Even in an environment that is unstructured enough to actually be able to do this. Okay, so over the past sort of 4 years, we've actually done a lot of deployments, and that is another thing that sort of sets us apart from the rest of the crowd. Now, this sort of being a BCS talk, I would like to very briefly mention this. I'm not going to talk about the sort of in-depth architecture of what we do, but one thing that actually we found very interesting, apart from the multi-domain idea that I think you already have a sense of, and I haven't really talked about warehousing or anything like that, but because we don't use GPS, we can actually operate indoors as well, right? So we don't have a problem with that, even underground in mines and so on, right? But the other thing I would like to point out is this modular business, okay? So this is interesting, right? Because one thing that I found very surprising when we first started dealing with sort of bigger companies as customers, these guys will often be sort of software giants, right? Or even hardware giants. And they come in and they say, well, you're a software company, as in us, and we expect you to give us a monolith of a software package. And we have a thing, we have like a shell script that says, make autonomy. Enter, right? And that doesn't go down so well because these guys often have had development programs that run for a long time. Okay, and have cost a lot of money, and a whole lot of people like you and I, and we kind of empathize with that, have a personal affinity with the work done. I mean, we're proud people, right? We're engineers, we believe that the stuff we do works, and we're proud of that. So they have a whole bunch of people in their company who actually react badly to them going, actually, well, that stuff is not so great, we're just going to wholesale import this stuff. Okay? So we decided to do something different, and that wasn't so much a conscious decision, it was more a fact of how we develop, because we're a whole bunch of people like that. Where we decided to find sort of a middle way around the way that the system is architected. Okay, so we have, and I'll talk about that in a second, we have sort of a modular stack that can take in third-party inputs, and that does the whole thing from the raw sensors to through sort of the sensor processing, the inputs, the adapters, the navigation, the perception, the control, the safety, and so on. You can do the whole stack. But if it turns out that you're a company that's developed this, and you're really bad at localization, so you don't want the rest of it, you're really proud of your plan or whatever it is, right? You're really bad at localization, you can have our localization module. Right? We can take that out of the stack and we can hand it to you, we can wrap it up, and I'll talk about that a little bit. And you can have that, so you can use it for benchmarking. Or the perception module. right? Or any of the modules inside it. So we'll talk about that a little bit more. So this modular bit is really, really, really quite important. Right? Okay. The autonomy adoption curve. So everybody will have heard loads about this, and I'm pretty sure most of you guys will have a different opinion from one another on how this should play out. Okay? So I'm showing you this for two reasons. One, I'd like to frame the conversation with this a little bit, and then I'll point back to kind of how we're different from some of the crowd, right? Or actually all the crowd. Today we're kind of in this place, right? We read a lot about trials and sort of closed environments. These are typically one vehicle, maybe a couple. Very few companies have bigger fleets that go around and do this, but these are typically sort of closed environments: campus, airports, warehouses, factories, few trials. Okay? And then at some point in the future, for us, the very, very near future, we'll talk about that, we still operate sort of closed environments, and by closed, I would like you to think of not as fenced off, but geographically very well defined. Okay, so this could be a street, it could be a campus, it could be a route, right? But very well defined. Okay, and some sort of service rollout around that, right? And then those regions tend to grow, so we kind of eventually grow those out, and then we have these sort of mobility as a service operations at a sort of larger scale. And eventually, there is this brave new world where we reinvent mobility, and nobody's going to own a car anymore. There's pay-as-you-go driving, final mile delivery, and so on, mobility on demand, all that stuff that everybody always promises you, right? And I think, broadly speaking, that is right. We can now argue about when what happens, which one of these things, right? Some things are well defined, others are not so well defined. But here's the other thing: put yourself in the shoes of Silicon Valley investors, okay? And this is now a pitch, right? And I'm going to come in and I'm going to say, actually, this is the autonomy adoption curve. And somewhere up here is like many trillions, right, of dollars. And that's the holy grail. And I'm going to set up down here. And the plan is that I've got the world's best technology, and I'm going to go dark and tinker with it and hire like 300 people. And we're going to go all the way through this until we get here. And round about here, we're going to go public with our technology. And you guys are going to get the biggest cash-in ever. Please insert $200 million here. Okay? That's sort of the kind of pitch that happened around there. And back in the day when my partner Paul Newman and I sort of thought about setting this up, we thought actually it's a pretty stupid model for two reasons. One, nothing happens for a long time. Two, there is, if you only think about on-road driving, yes, there is a world where you can only focus on this problem, you try and solve that, and you kind of go dark and you push it through. Okay, fine. But also, think back to what I just said about there's so much more to be done other than on-road driving, right? Imagine you all these other domains as well. Then actually what I learned about autonomy in a mine or in a warehouse or in a port, I can use literally intellectual learning as well as actually machine learning. I can use this stuff to bootstrap all the other things that I do. Okay? So just focusing on one thing and going dark on that area is actually not so great, because deployment begets better technology, right? Which begets more deployments, which begets better technology, right? So there is a world, and this is very much the thing that we feel passionately about, where we start down here, and all the way along this curve, there are little offshoots. There are little offshoots that come off this arrow, right, off this curve. That means we can monetize a particular thing, right? So, for example, think about this question of where am I, and this will make a lot more sense in a second, being one of the core questions, together with what's around me, right? Forget autonomy for a second, but imagine you are British Rail, and it turns out that on balance, you don't know where many of your assets actually are in and around the rail network. If you know where you are along a rail track, and if you know how to classify these things or detect particular types of objects, there's a lot of stuff you can do in terms of information management and asset management, right? Imagine you're a company that specializes in building information management. Imagine you have a handheld unit that has the same technology on it. You go around, it's exactly the same stuff. And this is the beauty of it. For us, it's the same technology. We don't really change much. And so from a software engineering point of view, the thing that is actually very difficult to get across sometimes, but is very important to us, is in our different deployments, for us it's all the same tech, we write one software stack, that kind of deals with all these different domains. And it's modular, so we can stick it together in such a way that, yes, we can probably provide a thing that does building information management if we had another 300 people that actually work in that sector, right, in terms of deployment, not in terms of core technology. That's why I also wanted to show you that particular code. Okay. Right. There are many, many ways in which we can skin this cat in terms of our technology offering. I've chosen one particular one, and we typically tend to split this up into two separate things. Okay. So on one hand, we have sort of our core product stream, which is sort of Selenium, which you can think of as the full stack system. So that only lives on the vehicle, one vehicle, based around onboard sensing only, and literally does the whole thing from raw sensor input all the way through navigation, perception, planning, control, safety, actuation, and so on. And I'll talk a little bit about, I talk quite a lot about some of the components that go in here. And then on the other side we have, or rather somewhere in the cloud, we have Cesium, which you can think of literally as a fleet management system, if you like, though you would do it in this service. But think of it as a fleet management service. It's sort of the cloud-based system that sort of oversees all the vehicles. But that's sort of interesting because fleet management systems exist. Fleet management systems that are in some way aware of the fact that they're actually managing a fleet of autonomous vehicles, more difficult, but actually very interesting because you can use that sort of coordination in order to improve some of your autonomy. Right? And that will make a lot more sense in a minute when I talk about what we call the experience paradigm, the vehicle experiencing the world. So you can imagine that you have a lot of experience in some parts of the world, you don't have that much experience in other parts of the world. So you can actually do something about that. Okay, all right, but we're mainly going to focus on the signals. All right, so I'll show a little bit of a system diagram. Always goes down well, particularly with the BCS, I hope. Selenium is sort of the thing in this gray box. I already said it sits on the vehicle, so that's what you kind of have here. Right? In Selenium, there's a couple of things I'd like to point out about this diagram. Right? So, firstly, there are a couple of sort of core problems that we deal with, which are these blue lozenges. We have the localization of the navigation, where am I? We have perception, what's around me, planning, what do I do, control, how do I do it? These are sort of the core problems that you have to solve if you want to do mobile autonomy. Anything that's moving and is trying to achieve a particular task will have to solve these sort of problems, right? Answer these sort of questions. And I'll say a lot more about that in a second. The other thing that I'd like to point out is, and so Selenium kind of sits here, kind of via Cesium, and then talks to, for example, other vehicles or third-party providers of services or input to this whole thing is a bunch of sensors. We don't make them, we buy them. Okay. In fact, we try to stay as close to sort of off-the-shelf components as we possibly can, because ultimately, when you kind of build a market product, you want the supply to be relatively easy, right? So we try to stay away from sort of custom-made hardware like that. This is kind of interesting because you know how I said earlier that people get really, really attached to their own software and their own way of solving things, and they react badly if you just say, actually, wholesale, here's the thing. This is a valve that also helps us release this. So imagine that you are an enormous tier 1 supplier, right? Automotive tier 1 supplier, and you've just spent 20 years writing the world's best white line detector ever. Okay? And you're very proud of it, quite rightly, because you know it's a good thing. And you would like to use that thing somehow, right? The answer is you insert it here. Okay? The answer is this is sort of a valve that allows you to insert information that comes from your particular deployment area, from your particular area of expertise. It might be something really complicated that only you can do, right? And the idea is that we can leverage that as part of the Selenium stack through a fairly sort of standard interface. Okay. Now, the next interesting thing about these lozenges is each one of these we would call a sort of a competency, okay, a thing that you need to be able to do. But for each one of these, we can produce a whole bunch of these. Or actually, the other thing I should say, as regards to the sensors, we consider ourselves as sensor agnostic. So we try to provide full stack solutions that are based around vision, actually, and laser, and radar, but you don't necessarily need all three. So we typically tend to integrate all three depending on the application domain, but you may find yourself in a place where you're saying, I'd like an autonomy system that operates in a warehouse, but that warehouse has no lights. Camera is not the best option for that particular thing. Okay? So you might choose to use a laser, so we can do that. But at the same time, you might be somebody who really dislikes active sensing. Actually, a camera might do really quite well in that particular environment. Or you say, actually, I have the need to look a long way out. I need a sensor that can see not just through stuff, but actually can see a long way. So radar might be a very good candidate here. And of course, they're complementary. And I can spend another day or so talking about how combining them is a good thing. So we're kind of sensor agnostic because we try to answer each one of these questions with each individual sensor, but also with a combination of them. Okay. All right. Now, the interesting thing about this, for each one of those lozenges, we have a bunch of these. Where, for example, you might say, and I'll talk more about this, knowing where a person would drive right now in this particular situation is a useful thing. Okay. That's a perception competency, right? That's a code module. It's actually an executable that can run that kind of communicates with the overall system. But it's one of the competencies in the perception stack, right? Look, and then we have the same for localizing, for prediction, for planning, and so on and so on. So again, if you're somebody who says, actually, we already have a pretty good, stack solution, but we have holes in particular places, we can reach in and break out any of these. If you're saying, actually, I don't really care about autonomy, but I really care about knowing where my fire extinguishers are, okay? Again, we can just break out one of these. In fact, and this is an interesting thing. Okay. In fact, we can take our entire vision-based navigation system, which is, I would certainly say, but I would say that the best in the world. And I can say that because I have nothing to do with developing it. It's totally some of that from there. We can take that, the entire thing, and not run it on 16 Titans in the back of a vehicle. Okay? What is this? Right? So that thing runs our entire vision-based navigation stack. And that's kind of mind-blowing because typically we live in a world where a lot of money gets inserted because you've just done your big pitch to your venture capitalists, okay? And they've inserted a lot of money, so you've gone and you've bought a vehicle, and that vehicle you have decked out with a whole bunch of blades and a whole bunch of Titans and a really big air conditioning unit. Okay? And potentially a little trailer with like a mobile generator, doesn't it? So the interesting thing for us was that we decided in the beginning we didn't want to do that. So we came up with ultimately what morphed to this notion of AI hygiene for us. We were trading from day one, so we kind of sold product from day one, which meant we couldn't really go to a place and say, here, all you need is this enormous compute power. So from the get-go, our software development was such that we were able to ultimately bring it down to something as small as this. And it makes for interesting conversations with chip providers, because they come in and they go, we've taken this enormous thing and made it smaller, but it's now more powerful, and you really want to buy it because it's everywhere. And contrary to that, we would then say that we've just downgraded our compute power. We take pride in being able to do that. That and the conversation where somebody went, and where's your air conditioning unit? And the answer is actually we don't have special air conditioning because we don't need it. Okay. All right. Much more to be said about that, but I start to ramble, so stop me if you find that's happening. Okay, right, and Cesium, fairly vanilla at this point, so cloud-based system. Interesting because this is kind of what allows us to do the cybersecurity bits. Standard stuff, API to enable sort of third-party interfaces, so think of booking systems or logistic systems or anything like that. Map update sharing between vehicles, so clearly the vehicles communicate, right? And again, when it comes to experiencing the world, these experiences can be shared, that's important. And this kind of thing down here is kind of cute. So real-time insurance in the loop, which is this notion that often people think of, particularly insurers, think of insurance being an afterthought for autonomy. And that's not really the case, because if you go to your insurer and you buy car insurance, they look at your driving record, they look at the car that you buy. And if you are like me, your insurance is going to be really cheap because your car goes like at 3 miles an hour. Okay? And then that will be valid for a year. Okay? Doesn't really make sense here because typically, and we will see this happen in a minute, the performance of the system is very dependent on the environment you operate in. And not just on the environment, but also on the environment conditions. Okay? So you need an insurance system that is actually a lot more agile in this particular case. And we've done a lot of work with XR Kaplan, our partner, or AXA XL as they are now, to kind of explore that space in a project called the Driven Project, which is actually super interesting. Anyway, so that's sort of cesium, but if you're okay with that, I'll now talk a little bit about the technology. Is that all right? Yeah? Oh, good. So I'm going to break this out into the things I've said several times already, the where am I, the what's around me, the what should I do next. Okay? And I'm going to start with where am I. Before I get to that, here's a bit of a prologue, and actually before I get to that, who here works in machine, or has any experience at all with machine vision? Yeah, okay, good. Okay, good, I can work with that. That's great. So you might find some of these bits a little bit boring, okay, but that's fine. Okay, so let me start this again. What we see here is basically essentially a visual odometry system. This is about ego motion estimation, okay? So imagine I buy a thing that's this, it's like a golden brick, and it's got 2 cameras in it. What we see here is 1 frame of each camera, okay? And we know this line really well. It's really well calibrated. The cameras are calibrated also very well. And what you see in each one of these frames, these kind of dots that sort of pop up, right, are things that the machine somehow finds interesting. Okay? And it's different from what you and I find interesting. What machines find interesting typically are things like corners, right? Gradient sort of things, right? So we're not talking about sort of clowns and pink outlines. But the interesting thing is that it kind of picks these out because it believes that somehow it might be able to relocate them from a different point of view. Okay, let me start this again because it's playing with the All right. There you go. So that's sort of the green and red dots that you see, right? And so what the machine does is look at that in both images. It looks at both images, finds these key points, right? Finds some way of describing them such that it can recognize them from a different point of view. And then you see every time you see like one of these blue lines, it matches them across. Right? So it says, actually, I believe this guy here is the same as is the same as this guy here. Okay? And it can do that for a whole bunch of things, all the green ones. It can't do that for some others, all the red ones. Okay? But if we do that for enough, it'll get a consistent view, because these images were taken at exactly the same time, it will get a consistent view of how far that particular point is away in space. It's triangulation, right? So, because we know that baseline, we can see how far that point is away in space. Okay, great. Now, this is a video camera, or these are 2 video cameras, so I can get a video stream from each one of those cameras, and I can do that exact same matching trick, but not just across images, but also through time. Okay? And what I get then is something down here, where this is sort of a 6-off coordinate frame, where somebody basically took a camera like this and went, in this case, around Chapel Court at New College, literally just like this. Okay? And so from that, we can estimate how the camera is moving through space. Right? And that's kind of interesting. So many people have done that clearly before. Doing that robustly is a real engineering effort, and I'm very delighted to say that the guys at Oxbotica have managed to do that really quite well. In fact, so well that through an independent trial for the European Space Agency, that particular piece of software, broken out, was selected for the ExoMars rover that is going to go to Mars very soon. So that's sort of an interesting conversation to throw in when it comes to contracting. We have galactic aspirations. Different. All right. So that's kind of how we estimate ego motion. Now imagine you've got that system and you plug it onto a car, and imagine that you put a fake taxi cab cover on it. That's really important. Doesn't work without. And so you fix that to the car, and down here, for example, it doesn't have to be there, but somewhere on the vehicle is another sensor, like for example, a laser scanner. Okay, who here knows what a laser scanner is? Okay, so in this case, it's actually a 2D one. Typically now we use sort of 3D ones. When that picture was taken back in 2011, 3D ones are really freaking expensive. A laser scanner is basically the same idea as one of those laser pointers, right? If you do DIY and you buy one of these guys, you can point it at a wall and it will tell you the distance, right? Now, a 2D laser scanner basically does that with a distance measure, and it also gets intensity of the reflections back, right? But it will press that button about 180 times per scan. In this particular case, it will scan like this, okay? And it will do that about 50 times a second, yeah? In this particular setup. And so that means you kind of get a fairly dense representation of what the world looks like in that case. Okay? Sparse compared with an image, but fairly dense. But the beauty of that is, because hopefully your car or your form factor vehicle is rigid, right? Which means that if you know where the camera is and you calibrate that really well, you know how the laser is moving as it's moving at the same time as the camera, right? And the interesting thing is when we talk about calibration, typically we kind of draw this arrow and we think measure stuff in units of centimeters and millimeters and millimeters and whatever. But actually, microseconds are really important in this case, right? So aligning the data in terms of time, really, really quite important. And again, the guys have photographed some extraordinary stuff. All right. Okay. So we can do that, and because we now know how the laser is moving, because we know how the camera is moving, we can now do something quite interesting, right? So we can actually get sort of almost survey grade, centimeter accurate 3D representations of what the world looks like just by driving through it, right? And that's kind of interesting because there are people out there who set up companies around the fact that they build 3D maps suitable for autonomous driving. This is kind of what we call the exhaust of our system, right? Because it just happens at this point, which is sort of a beautiful thing for us. And you can see now, I haven't got a video of that particular thing, but you can see now, this here, for example, is part of Milton Keynes, and the reason why you see sort of color in this is because we know where the laser is with respect to the images, with respect to the camera, right? And because we have that calibration, we can project the laser measurements into the camera image, and of course we can then just look up the color that place in the world should be, right? That's not how it works. But the interesting thing here is that if you look at this being Milton Keynes, this is inside a warehouse. So this is literally just somebody driving a forklift truck with some of our tech on around the warehouse. This is a purpose-built racetrack in London. Does anybody here know about the Shell Eco Marathon? That was sort of a cool thing. It's like a student STEM thing. So we automated that, which was super fun. But you can see how we can take that sort of tech, nowhere near autonomy, how we can take that sort of tech and stick it on a train, for example, and get a really good idea of what the train track looks like, right? Or on every dust cart, rubbish truck in Oxfordshire, because you want sort of a high fidelity idea of what Oxfordshire looks like, updated every week, for example, right? So you can get a sense of that. Okay, so this is one way of looking at a map. There is another way of looking at a map. So this is again this enormous map of a warehouse, but this is sort of a 3D point cloud derived environment. So I can click on any point here and any other point there, and I will get an actual distance measure back. Okay. There is another way of representing the world, and that's actually to do purely with video. Okay. What might that look like? Well, have a look at this. So this is a super cool piece of work. Again, when I say that sort of stuff, this is typically not done by me, okay, just say. A super cool piece of work, actually, very, very effective. And what you see here is, initially, videos that are set up in time. They're aligned in space. So this is the same place. Every cell shows the same place, exactly the same place, but at different times of day and in different environmental conditions. Okay? And you can see that there's enormous range in doing this. Now, this is also a valid representation of the world in some ways, right? The question, though, is how do we use it? And that's very interesting, right? Because initially, you might say, well, actually, that should be pretty straightforward. I've shown you this stereo matching trick previously, right? Well, forget the second camera, just use one of them, right? This is your live view. You go around once, you record that memory, so you record a video stream, right? And then you go out again, and then you pull exactly the same matching trick, okay? Job done. And many people have tried this. And that works really, really well, as long as your second outing happens within a few minutes of the first. Okay? Why? Because of this. Right? And this is, again, this is sort of the same idea. This is a very early version of our test track out in Bedrock. Same place, different environmental conditions. Okay? And so this is typically where it goes wrong. So if, like me, so I'm sort of a machine intelligence, machine learning kind of guy by heart and by nature and by background. If you're like me, sort of many years ago, you would have looked at this and you would have said, well, actually, what we need to do is we need to build a model. Okay, we build a model and then we perform some inference. So in order to do this, I mean, inference is difficult, right? So we're going to call it inference. It's going to be approximate inference, okay? So it's going to be little errors here and there. And our model is going to help us in first stuff when it comes to what this place looks like when it's raining, and when it's sunny, and when it's overcast, and when there's a particular shadow, and when it's snowing, and when the shadow looks a bit weird, like around 1 o'clock, right? So when it's 1 o'clock, and when the leaf is a bit further over here, right, and so on. And the problem with that is not only that the inference is approximate, typically. The problem is also that I have to enumerate all the things I want to model, right? And this is typically where this sort of thing falls apart. Because if there's one thing I've learned in doing this is you cannot possibly write down all the things that happen in the world. Okay? Now, interesting thing. Along came a guy, and the guy really driving this work is Paul Newman. Along came a guy, one of his PhD students, very clever, very, very nice guy. His name was Winston Churchill, literally. Most people didn't quite believe that paper anyway, but it was a true story. And he came in and he one day said, you know what, all that inference stuff is great, but what if we just record everything? Let's just record everything. And that raised some eyebrows, because the idea was, well, so if that is true, that would imply that there is some structure in the world, if that did work. And of course, it seems like such a simple idea. People clearly would have done this if it worked. Okay? So Paul and Winston at the time decided to run an experiment. So they said, Winston, take a car, go out 3 times a day, 3 times a week for 3 months. So capture some variation in season and in time and so on and whatever. Record all things, and then run an experiment. How many of these, and so each one of those video streams, think of that now as an experience. I'm going to call it an experience. Okay? Record all things and find out whether at any point you can localize well, right, throughout a prolonged period of time. And so 3 months later, I'll come to that in a second. 3 months later, Winston came back. Actually, I'll show this. 3 months later, Winston came back. This was our test track at the time, and says the answer is 33. After 33 experiences, I never get lost. Which is, at the time, was just mind-blowingly extraordinary. Okay? But okay, I'll get to that in a second. Now, why is that interesting, right? So, imagine you live in a world where you have sort of 2 dominant colors, sort of red and yellow, right? So you get this sort of world, okay? And this is the visual geometry. That's the ego motion estimation. It's running all the time, right? And it's just kind of running and running and running. And imagine you already have 2 experiences, 2 video streams locked away, the yellow one and the red one that you have from somewhere, okay? And everything's hunky-dory, and you've got one parameter in your system that says, I'm going to feel great about myself as long as I can localize myself against 2 experiences. Yeah? And that's great, because in the yellow and red world, life is good. You can localize the yellow, you can localize the red, right? Just forget what you see, because localization works really well. And then an evil thing happens, because yellow disappears from your world, and please don't start arguing with me now about green being a mix of yellow and other things. Okay? So yellow disappears from your world, and instead this green thing appears. Okay? So your condition is now no longer met. You no longer localize into 2 particular experiences, but only into 1. So at this point, your vehicle will say, actually, I can't operate you, and your condition isn't met. I need some help here. Essentially, it means somebody to drive me. Right? But while then somebody's driving you, or driving the vehicle around, this green stuff gets recorded. Not because an operator has pressed a button, but because the vehicle decided that actually now needs to record what happens, because clearly it doesn't know enough about the world. Okay? And at some point, green disappears, and we get back to sort of red and yellow, all is good, and so you stop recording this, and you localize into those things. But the interesting thing that happened was that this now is the green experience. Right? Next time you come around, what happens is that you might hit this red and green place, but you now have a green experience, you have green and red, and your condition is still met. Right? So the vehicle, through trying to achieve a particular task, builds up a chest of experiences that it can refer to. And that's sort of really, really important in this particular case. And of course, yes, we can talk about how these experiences can be shared across vehicles, and so on and so on. And so that's also how it scales to large environments. Okay. So that's sort of how the idea of this. And so Winston went away and kind of did this around this test track. Came away and basically said, after 33 experiences, life is good, I never get lost. Okay? And he kind of produced this color-coded thing, and everybody in Oxbotica is going to be horrified that I even show that slide, because it's very, very, very colorful. And I think it makes the point really beautifully, because if you look at this color coding, blue means few experiences. Okay? So along this road here, I only ever needed of the order of 5 to 10 experiences throughout the entire time. Why is that? Because it is the single most boring road on the planet. Nothing ever changes. It really doesn't matter what the weather is like or what time of day it is. Where it gets a little bit hairy is this place down here, which someone wonderfully calls the corner of doom. And of course we've got the satellite overlay and those guys kind of sitting close to the front. Do you have any sense of what's going on there? Trees, exactly right. So trees are wonderful. Bloody annoying when you want to do computer vision though. Because when the sun shines, which is rare enough, thank God, when the sun shines, they cast shadows, right? And those shadows move. But here's a really interesting thing that this sort of work I think brings out really quite nicely. The way they move, if nothing's broken with the universe, is actually structured. So if I take a picture now and I see all the shadows and I come back 3 hours later, it's going to look very different. But if I come back tomorrow at the same time, it's going to look really similar if it's sunny, right? And that's really but that's really an interesting sort of thing that came out of this. And that's also why this works, because ultimately we capture the number of different faces that the world tends to show you in doing this. Okay. And of course,
we don't have that. Is there a minimum time frame of what people do?
So, in a way, yes and no. Okay, so we have ways of making that bit more robust in the sense that we can span a larger amount of time, and that's sort of the thing that you see. These are sort of the blobs here. The blobs here are the hour equivalent of the little dots that I showed you earlier. Right? That's one answer to that. But ultimately, what it boils down to is sampling. Right? So, for example, you want to run this in a warehouse. Let's just assume. Okay? And in fact, there is work in the warehouse. Let's assume you want to run this in a warehouse. These things are meant to change, and you would be perfectly legitimate in saying, well, everything changes. That's the nature of the warehouse or a car park. Right? And so if you had the system on a forklift truck that goes in one day, and then all the forklift trucks for the next 24 hours change everything around, and then it comes in the next day, it may well not work. In all likelihood, it won't work. It won't be able to localize because the world looks totally different. But if the agents of change in that environment tend to be carriers of this technology, so if all the other forklift trucks, or a significant proportion of all the other forklift trucks, also have this sort of system on board, you sample the environment frequently enough such that the amount of change doesn't influence the system. And when it does, you build up more of an experience. And so by doing exactly that, this is working in a warehouse, and I'll show you lots more examples of that in a second, but by doing that, we can string, or the system can string a series of experiences that take you all the way from early morning, from dawn, through the day with all its variations, through dusk, into night, through the night, and back into dawn. And that's what I mean with the sampling coefficient. Yeah.
Is that how the experiences are correlated, just against time? You say that you need a minimum of 33 experiences.
Yeah, so that's only for that one. That's only for that one environment. So one thing that relates to this question that people typically say is, well, how many experiences do you need? And my answer to that is, what environment? Like what kind of environment is it? If it's a car park or a warehouse, if there's frequent change, it may well be that we need quite a few.
Yeah.
If there is no change ever, like on the world's most boring road, then we need like one. So the London Eco Marathon, we did with 2 experiences because that was kind of awesome, but kind of really boring because nothing much happens on the racetracks.
Around the whole.
Yeah, we needed 1 in sun and 1 in rain.
Okay.
Yeah, that was basically it.
Sorry, just one other thing on the basis of that. In a structured environment such as a warehouse, why would you necessarily rely on using the sampling from a moving object when you could potentially do it from a number of fixed objects?
Yeah. So you could absolutely do that. There's nothing necessarily saying that it must be a moving object. That is a true thing. Typically, we tend to deal with vehicles in that space, and people are interested in sort of automating these. And if you have sort of, I don't know quite what you're thinking, but if you're thinking of like a set of beacons with sort of technology on them, for example, for us, I would count that as putting infrastructure into the world. And that is something that we don't really want to leverage. Right? So, and why? Because the other question in that vein would be, well, why not just build the warehouse in such a way that it's useful to you in this context, right? Which is a very good point, and of course Amazon did exactly that, right? But if you're, Joe Smith with 2 warehouses and you're really proud of them, you can't actually afford to rebuild everything and shut everything down for a bit and then rebuild it in such a way that you can automate it. And in that case, you actually need a solution that can solve the problem that you want to solve. In this case, it might be automating, even if not all, some of the operations in the warehouse for sort of at a cost-effective price point. Okay. All right. So these are kind of just use cases now. And everything conceptually, what I've just explained, that's exactly what's going on here, right? So here's sort of the live stream. Here's sort of the map reference. The bit that I showed you with stereo earlier. This is sort of the same idea. The red and green dots are replaced by these sort of clouds. These blue lines are the matches. We do a little bit of magic to remove sort of shadows to some degree in grayscale. And what you see here is how the vehicle is moving relative to a reference trajectory. Okay, so what that means is that somebody can go in, drive a forklift truck along the route that it is meant to be driven, and that doesn't have to be just one route, it can be a network of routes, right? And then ultimately, the vehicle knows what kind of routes it's meant to follow. Somebody will then annotate them and say, over here is drop-off, over here is general pickup, and so on, loading bay, whatever. And the vehicles then operate relative to that network. And that's interesting because at no point have we put anything in the ground. So that's interesting in the context of the port, which I'll actually get back to. So let me put that on the stack for a second. Okay. Here it is, sort of working in different environments. So this kind of underpins a lot of the stuff that we do, almost all the stuff that we do. These videos are sped up before anybody gets upset that this is very fast. It's for. I've kind of talked about this. Of course, we talk about urban quite a bit, but rural is sort of equally important. Some might argue more important. Bad weather. So California is beautiful. That's great, but also part of the problem because you don't quite get the variety of what we see here. And of course, we can spin that further. So we've operated on a number of different continents now. And so we do anything from sort of rain and sometimes snow, sort of in Oxfordshire, to continental Europe, sort of to typhoon over Asia, right? And so we've kind of got experience in all of those sort of areas. And I think, as far as I'm concerned, and again I can say that because this is totally nothing to do with me, I think that's one of the most robust and therefore one of the most exciting real-world engineering systems that certainly I've had the privilege to witness. Okay. And of course, it works off-road. Why? Because at no point have we said only look for white lines. And that is an interesting thing. It's very interesting, actually, in a few minutes, but let me make that point here. Imagine you're a car manufacturer and you're really, really keen on providing a thing that is called the, self-driving captain, okay? And your business model is to say, we're going to automate highway driving, right, motorway driving. And it makes perfect sense at that point to say, you know what, clearly motorways are very well maintained, okay? People spend a lot of money on painting the correct white lines onto motorways, right? So let's start by looking for the white lines. From that we can back out where the lanes are, so then we know where to drive. Okay? Makes perfect sense. The problem that we have with that is that you've just impeded your own path, excuse the pun, to L5 autonomy, because the vast majority of the roads in this world not only are not marked properly, but they're most likely not even paved. Okay? So in taking that particular approach to solving the problem of where am I and where should I go, you've kind of impeded your way forward. And so for us, this multi-domain stuff kind of acts as a regularizer, right? It sort of keeps us grounded in a way that we generally answer these questions: where am I? What's around me? How should I act? In such a way that we can deploy this into different kind of scenarios quickly. And this is why we can do this. This is exactly the same system running off-road. Okay. And again, here we see this. So again, same system running the airport. We've already seen the Port of Singapore, and this is something that is worth shouting out because the Port of Singapore is autonomous in a way, right? It's got autonomy running. But the way that is done is via breadcrumb markers, RFIDs, in the ground. Okay, so somebody dug up the tarmac, put the things in, and put it in. And that's a great solution. It worked really well for very, very many years, and it still works really well. But the problem is, if you want to change the routes that you go past, you're kind of screwed because you have to dig up the tarmac and put more RFIDs in, right? And Also, if anything ever blocks the route, you're equally screwed because you can't go around, because there are no RFID markers around, right? Whereas with the system that I've just outlined, you basically get in. If you want to teach the system a new route, you drive it. You're done. Okay? And then, of course, there's the planner on top of that, so you've got the new reference route, but of course you can deal with obstructions and everything else. Right? So that's a really useful thing, and that's what we're engaged in talking to these guys. Right. And, I've talked about mining. You get the point. It works really well. Okay. So, who here works in object detection? Out of interest. Anyone at all? No? Okay. All right. I was kind of debating whether to leave that slide in, but I think it's a really cute sort of illustration. Now, when we talk about what's around me, basically we talk about perception, and people come and go, can't the vehicle just see? Surely. Right? And then I'd like to show this. What a vehicle, what a machine sees when it sees an image is actually this. Okay? A whole bunch of numbers. And I suspect potentially if you're sitting slightly further back, can you tell me what that is? Yeah? Carrot. Good. Excellent. And I kind of left you with a bit of a chance because this is a very sparse sort of image. Okay? Now, the interesting thing also is it's only a carrot. Have a go with it. Anyone? Any takers? No? Okay. It's a cat. Of course it's a cat! Come on, it's a cat. But not only that, it's actually a white cat. It's sort of, it's got fluffy fur, it's probably super cuddly, my kids would love it. It's outdoors. It's probably autumn because it's running around on a bunch of brown and yellowish leaves. Okay? There is so much information in that image that we can identify, that we can make sense of because we can draw on a whole bunch of useful background knowledge, okay, and some contextual information. And of course, machines are getting better and better and better at doing this. That's okay. But no, actually, the machine can't just see because just seeing is really, really deceptively hard. Okay? Knowing what is in the world is something that we are tremendously good at, spookily good. Okay. Right. So what do we do? Well, okay. We're going to solve this by looking at a hierarchy of things. What is rule number one? Rule number one has got to be don't hit stuff. Yeah? Okay, all right. Now we can deal with that in a fairly robust way. Okay? We can use some sensors that are specifically certified to be good at detecting stuff. Laser scanners, for example, and you can get those with safety certifications, right? They're meant for this. And then we can say, well, actually, at this point, I really don't care about, cat or dog or anything like that. I just care about stuff. Hitting stuff is bad. Okay? And this is sort of what this does. So this is sort of a particular illustration of this where we kind of segment out in 3D different pieces of stuff. And of course, I kind of say, whether it's a cat or a dog, I don't really care about, for the same reason that I said solving machine vision with inference in this particular context is tricky, because I have to say what I care about, which would be cats and dogs. And do I care about people? Yes. Do I care about people with shopping bags? Probably. Do I care about tall people? Yes. Do I care about small people? Yes. Yeah, very much, right? But here's an interesting thing, and this actually surprised me, is do I care about dogs, I care about people. Do I care about the lead that is very likely to connect dogs and people? Right? The answer is yes, I really care about it, but actually I never wrote that down. Right? So again, I have to enumerate what's out in the world, and that's difficult. So at this level, I don't care about what it is. I just care about stuff and not hitting it. Okay? So that's interesting. So we don't hit stuff, that's great. And this is, at this point, very robust. Right? So if we look at machine vision, and I'll say some more about that in a second, again, it's inference. And it does go wrong, there's no doubt about it. It does go wrong. So let's build a system, let's engineer an architecture that is robust in the full knowledge that at the level of this is a cat, it will go wrong at some point. Okay? And this is sort of the baseline of it. Use sensors where you don't perform any inference at all that are certified to detect it. Okay. And they do that, of course, by physically touching the world with photons. Right? Okay, next level up is what do I care about? Well, what makes a difference to me? If there is stuff in my way, and that stuff is stationary, that's a bit of a bummer, right? Because it's in my way. So either I move around it, right, or I wait. But if that stuff isn't stationary, that's kind of cool because I can just wait because I know it's moving out of my way. Right? That's a valid action. So knowing whether something's moving or whether it's stationary changes the way that I behave. Right? And so the next level up from this is deciding whether the stuff that we've seen is moving or stationary. Okay? And again, we could solve that with particular sensors. So radars will do this for you in sort of a physically realistic, like in a real way. Or we can do that with a bit of inference. That's also fine by that level. Where we kind of okay. Right? And only then, in this particular 3D point cloud example, do we care about what stuff actually is. Right? So at this point, we switch to sort of more standard machine learning approaches where we say, well, actually, all these robots tend to be people, these tend to be cars, this sort of on the road, right? So you go along and you see a bunch of cars and a bunch of people, etc., etc. Right? So only at this level do we do this. Okay. And of course, if you have seen anything in the past sort of 5 years, you should not get excited about videos with boxes drawn around them. Okay? Because yes, this is kind of cool and it kind of looks awesome, and frankly, my life to a large extent is, and used to be, and still is about this sort of stuff. But that in and of itself, doesn't necessarily mean you can drive, as we've just discussed. Okay? But nevertheless, it is useful at a particular level, and of course, we can do that as well. But here's an interesting thing. If I asked you to produce an object detector for cars and show to me or prove to me that it works to some degree, right? You could do that. You could go home, download a video, download some software, run software on video, and make a video like that and go, yes! And about 10 years ago, you could raise a whole lot of money just based on that. Okay? Very commoditized. Now here's a different thing. So, because we have the full system, we have the localization of where am I, the what's around me, and how should I act, there's a whole lot of stuff that we know about the world. We know where we are in the world. Right? We have very detailed information about what the world around us looks like. So here's a thing that you can't necessarily do just by downloading some stuff. Okay? We kind of start this again. So what you see here, and I'm going to stop it here. Okay? What you see here is clearly a wideband. Interesting. But you see these kind of funny purple boxes, right, with those circles around them, right? And so this is interesting because what happened here is that the vehicle's experienced that particular bit, it's built up a representation of the world. Either a machine or a human has gone in and annotated that particular representation of the world, so the map, right, with street furniture such as traffic lights. Okay? And so that's now interesting because the vehicle, because it knows where it is, can say, you know what, I know this is looking a bit weird, but I really expect to see traffic lights here and here and here, given where I am right now. Okay? And those circles that you see are sort of uncircled regions that kind of are laid around that, let's say, kind of in this region look. Okay? Why is that useful? Because actually it gives the vehicle, like you, because you know where the traffic lights are when you drive, right? Mostly. It gives the system a heads up. Right? And it very much constrains where to look. Because if I said, actually pass a traffic light, should be easy, it's only 3 colors, right? By looking for green stuff, not so successful, right? But if I say, actually look for green stuff, which is easy, here, right? It becomes actually a lot more plausible. And so the output of that is that these boxes are where the vehicle decides traffic lights should be, and the minute you see the boxes change color according to the state of the traffic light. Okay? And that in itself is interesting because that means with a system like this, which is a full system approach to perception, right? It needs all of these different pieces to it. We can pass traffic lights from as small as 4 pixels in an image, so from quite a long way away. Okay? And that really speaks to this notion of having a systems approach. The system has a lot to offer, particularly when it comes to this next bit of what should I do next, right? So this is something I still think is quite cool, even though it's by now quite dated for us. So what you see here is sort of a gold standard sort of 3-level, it's called a segmentation problem. So every pixel in this image, this is what the vehicle sees, okay? Every pixel in this image has one of 3 labels, okay? Red means really bad, okay? probably an obstacle, definitely not drivable, don't go anywhere near this thing. Okay? Blue means probably traversable, but actually for the purposes of this, I actually don't care. Okay? Green means if my favorite human were to drive me, this is where he or she would be driving in this particular situation. Okay? And that's really interesting because if I sold you this as a lane segmenter, as in look for white lines and the lane is the thing in between, this will kind of suck, right? Because we kind of can't be in the cycle lane and whatever, right? And this bit here isn't classified as where we'll be driving and so on. Yet, it's quite close to a lane detector because it kind of shows you broadly where you might be driving. And here's the really interesting thing. So these are the easy cases, okay? And I call them easy because if I had a lane detector, I, in this case, could look for the white lines and back this up. Should have what to frame that particular sort of road layout where the roads are marked properly like this. Because if you now fast forward to places like this, which you recognize as Walker Street and up in summertime, the white lines disappear, your lane segmenter is now screwed. Okay, you're done. Whereas this system, because it's sort of a scene holistic thing, it takes the entire thing. On this case, let's focus on this first. Not only knows that it needs to be on the correct side of the road. And by the way, these vehicles are manually driven. These are not driving autonomously at this point in time, right? As a or when this video is taken. The obstacle segmentation, even though it wasn't designed for that, is remarkably good. It knows to cross that line to get around that vehicle, try and do that in a rule-based sort of way. Right? It knows the vehicle that it's kind of pulling out, and then afterwards it knows to cross the line again to drive back on the correct side of the road. Okay? All without any lane markings. That's a pretty extraordinary thing to be able to do. And at the time that we did this, there was only one other company out there that could do that, and that was a company called Mobileye. Maybe you heard of those? Right, yeah, just at the time then got bought by Intel for like $13 billion. So that was interesting. And over here, and I'll play you this again, the reason why I put that up is clearly, and I'll talk about how the system gets trained in a second, clearly what happens here is these vehicles get trained by being driven around. And clearly the people who drive these vehicles around have learned to give cyclists some space, which makes me personally very happy because I cycle quite a bit. And you can see that by the vehicle kind of curving around us, right? So pat on the back for that. Okay, how do we do this? And I'm going to keep this brief because we're kind of running over time now. Well, it's a systems thing. Love the system. Okay, we know where the wheels of the car touch the ground, so clearly anything between that is vehicle, right? This is done on a gathered data set, so we know where we're going to go next, and we can do that because we've got ego motion estimation. We know. Okay. When we train this, our sort of data mule has another set of sensors, an obstacle sensor, so laser scanner, for example, that looks outwards, right? So we project that into the image. Everything above that, let's call that obstacle. You don't want to be in that place, like ever. Okay? And anything that isn't red or green is actually I don't care. Probably not an obstacle, but in this particular case, I don't care. And note that at no point did I ever say, no, hook this up to the accelerator and the steering wheel. This is not what happens. Right? Okay. But okay. So that's how we generate the data. And the beauty of that is that every time somebody gets in the car and drives around, this sort of data just gets created because we're systems engineers. We know this sort of stuff. Okay? And then you can kind of reach for your favorite segmentation algorithm or your favorite sort of learning model. In this case, it's a deep model, but there's nothing fancy about it. It's kind of a point I'm trying to make. And you can feed that in because you now have an almost unlimited amount of training data, which is actually what the problem often is in this particular thing. Leverage the system to get the training data, right? And the other thing that I should say is, so the training is entirely sort of self-supervised. And of course, during training, the vehicle has the camera that we care about and the obstacle detector, like the laser scanner. Okay? And what happens next is during deployment, I can only operate with a camera because that's a sort of still vision-based thing now. And I can basically come up with a mapping that produces that segmentation for me. Okay? And it works incredibly robustly. So in principle, I can run this off the back of your smartphone, right? Which is kind of interesting. And this is just saying it works in different environments, it works in different weather conditions, and so on. But if we take all of the stuff that I'm now very conscious of time, have talked about for the past, 60 minutes, we kind of get a very versatile sort of place, which we're very proud of. And this is really what we're about. We're about the breadth of all these things. So automotive, yes, and we all hear a lot about automotive, but non-automotive. There is so much goodness in non-automotive, and it's such so much market and so little activity in that particular space compared to on-road, and we want it all. Basically, what it boils down, which is great, and it keeps us very happy as well. The geeks are really. All right. Our systems have been deployed for a bunch of years. I've made that point. We can kind of skip that. And the one last thing that I'd like to say is that agility is absolutely everything when it comes to this. So, and by that I mean, if you're a fan of deep learning, which I am very much, I do a lot of that stuff, being able to translate from one domain to another is not necessarily deep learning friendly, so you need the right mix of technology to bring into this, okay, which we believe we have. And so the beauty of that is that it takes us about 30 minutes to sort of map the second largest port in the world. We can go typically from arrival to full autonomy in a matter of hours, and I mean few, like a couple of the world. Our systems power sort of 10 different types of vehicles in various fleets around the world. The number of domains actually from about 1 kilometer below the surface to about 54 million miles beyond that. And I could say something about the size of the maps that we would have for sort of mapping London and how much that would cost in terms of hard drive space. The answer is about 80 quid. So it's absolutely perfectly feasible. Okay? And I think I've now kept you for way long enough. I have rambled. You didn't stop me. That was your fault. Thank you very much, and it's been a pleasure.
Do you have some time for any questions?
Sure. Sure. Hello. Yes.
What happens with novel journeys where the vehicle's never been before?
So in principle, somebody has to drive a vehicle. In order
But
for
are
it to
competitors going to develop systems that work for novel journeys?
You know what? I'm not convinced that very soon that is going to happen. So I would venture the answer to your last question is not anytime soon. If what I understand by novel.
But once they solve that problem, they wipe you out, doesn't it?
True, but once you solve that problem, you solve autonomous driving. The beauty of that is, I'm okay with that because we just switch to all the other domains that we're already engaged with, right? Which also makes it special. But there's an interesting thing. So, yes, you have to manually drive a vehicle for it to start to experience the world in a particular place. But if you instrument every second sold vehicle, like all of our cars these days kind of have cameras on them anyway, right? Then between us, if we manage the data correctly, we've mapped, we've experienced to at least some degree the entirety of the UK, probably in a matter of not many minutes, with all of our car service, right? For example. So what's new for me doesn't necessarily have to be new for you.
Just similar point, but positions quite different. If I was to take a drone with stereo, videos and so on, and the same equipment mod that your car has, and to fly it across the route, can I use that data that would then later be used by a vehicle? So there's a military context, we want to definitely to vehicles country.
So the geek of me says I can think of about 4 different ways of doing that. I think the realist in the context of the technology roadmap that we have would have to say it would take some adapting to give you that bit, depending on what sensor you use. So if you use sort of a 3D type of sensor, this to some degree may well work.
I was just interested, you must have done so much testing with your cars. What kind of tests were memorable? What did you learn from those tests that you did with these cars? Significant ones, just a couple. I was just interested. So you must have done so many different things with it.
I've got some way to start.
Yeah, we can't hear the question.
Sorry, the question was, of all the testing that we've done, I'm going to paraphrase this, are there some memorable anecdotes and surprising sort of things that...
Yeah.
And the answer is, God, loads. So, things that stick in mind are one example that surprised me, which was about literally the leash, the dog leash, which was a thing that we didn't necessarily anticipate as a problem, but that is a challenge. The other thing is that, particularly when it comes to our friends from the press, because they are after sort of action shots, they tend to believe that just because we have an autonomous vehicle, physics doesn't work. And so Newton's laws no longer apply. And so we have people who try to get the shot of the vehicle just stopped, right? And so we had a couple of people literally kind of from an oblique angle who ran at the car, because they tried it a few times and it just worked and it was exciting enough. So from an oblique angle they kind of ran at the vehicle and kind of tried to sort of, it did stop, but he jumped in front about 30 centimeters where it was going. So it did stop and it was fine, and nothing happened. But you know, that was a borderline sort of human idiocy case. Yeah, I mean, one thing that I was really pleased with about the London trials, the O2 trials, was there were journalists on board. And I can't remember, it was like the Guardian or something. There was a cyclist that was cycling out. I think it was a cyclist that was cycling out from somewhere. And I think that was from something like that. It was some situation like this. The port slammed on the brakes, and the cyclist kind of went past, and then it kind of realized that something was weird, something was odd, right? As you do when you just about to run in the bus, for example. Nothing like bad happened, and that was a real win, because I mean the press coverage was wonderful because it was all about autonomy system, you know, saving cyclists and stuff. It was great press. But it kind of speaks to this point that when we think about autonomous vehicles, and we think about how they will change how we kind of operate in societies and videos and so on, and we look at the press, there will absolutely be points where vehicles make mistakes and where bad things do happen. We've seen this happen. Where we go, well, actually, if I had been in person, this would never happen. Undoubtedly, this would happen, and it has happened. But then there's also the flip side, so we need to then back ourselves as a society, because there will be the flip side where we're saying that actually, if we look at the statistics of accidents happening, if we as a community design and develop this technology well, and that includes the testing of it and the responsible rollout of this sort of technology, we would absolutely expect those numbers to go down. Anyway, this is probably more than
Yeah, no, that's good. Thank you.
Right. In terms of the element you said about having to go in and annotate certain elements, such as traffic lights, do you feel like when you can deploy something across different environments, you could potentially have variable levels of complexity required to annotate? So if you're in a closed mine, for example, where you've not got road users as an example, but then when you're in a constrained environment such as the highway, then you've also got to conform to some sort of digital highway code situation.
Yeah, absolutely. So there are many reasons for why deploying on almost all things other than on road in sort of urban traffic is a much more amenable problem, and that's one.
How do you handle the mood of the vehicle? Take my case, I'm driving down this evening. I was keen to get here on time, so I didn't give way to anybody.
But you realise this is recorded, right?
At no time did you exceed the speed limit.
Of course not. No. So what's your question? How do I get my car to drive like you?
Can you give the vehicle a driving style? Can the owner of the vehicle, whatever that means,
To the road.
Yeah. Or can the car learn to not drive like a foot? So the answer is absolutely yes. And again, it kind of it's a broader conversation about architecture and where behavior fits in. Behavior, the natural place. Engineering-wise, there are many places where you could fit in behavior. For me, a natural place of where behavior fits in is when it comes to optimizing the optimization problem that the vehicle solves, when it comes to where to go and at what speed. Okay? And that's interesting because we have many decades of experience in designing these systems. Right? So what we typically do is we hand specify a cost function, and the cost function, for example, will say hitting stuff really bad. Okay? But it might also say you want to drive in the middle of the road, preferably. You don't have to, but preferably. So the optimization will then find you the path that kind of does it. Now, that is interesting because at this point I have a very good lever that I can pull, which is the design cost function that makes the vehicle do what you would do if you wanted to drive like you. Right? And we assume for now that's a good thing. Right? Now, the obvious problem comes, how do I write that down? Right? How do I write down a cost function that does that? Like you, because you don't really do that, right? Now, first instance of that is insurances already do that in a weird sort of way, because if you ever go to an insurer and you ask how they determine the level of damages if you fall from a ladder at work and you kind of hit your head, turns out there's a table of stuff, right, that is somewhere where, for better or for worse, some people have a value is assigned to different outcomes, right? So there is a case to be made. But of course, the beauty of it is we don't actually have to do that, because there are systems out there. And I heard somebody in the audience outside earlier say they work in imitation learning. There are ways in which I can get vehicles to observe you driving and to back out the cost function that you are likely adhering to, such that I can get it to drive like you drive. So that is technology that we have. Alternatively, I can also get it to drive like people. But there is a personalization aspect to that.
Thank you, very fascinating talk. Could you possibly talk about the network efficiencies in terms of when there are like multi-robots like moving together, and how can we deal with this kind of problem? Especially we want to have like low accident city in the future, and when we deploy the drones.
So are you asking how autonomous vehicles interact, or are you talking about mixed data, or are you literally talking about data rates? Okay. Okay. I mean, basically, so there is an opportunity with vehicles, whether autonomous or not, to have vehicle-to-vehicle communication. That's a useful thing. Many people are working on that. It feels a bit daft to not leverage it. Our technology is designed to not depend on it. Just like with GPS. So I said we don't depend on GPS, which is super true. Which is true. Yeah. But if it's available, it would be nuts to not leverage it, right? So you want to be able to be receptive to that sort of thing. So in this case, there are mixed environments where it's humans and people, so where it's humans and machines, or where it's when you live in a world where there's a fully automated world where you have only autonomous vehicles around. It doesn't really make that much of a difference. If that even goes anywhere near answering your question.
Really long question, but how would your vehicle deal with, like, say, a small pile of snow or a branch or roadkill? I don't know. Would it stop, or would it? How is it?
It depends on what.
Would it know that it's okay to go through, or?
So it depends on what it looks like in the sense that typically you're making a conservative decision, and that of course is part of environmental bit that engineers and customers say that autonomous vehicles tend to be very conservative, very, very conservative. So they would not do what we described earlier. They would not typically go and sort of drive sort of aggressively, not that you do. So it depends. In all likelihood, it would stop as long as it has an obstacle.
So a hedgehog versus cat, for example. Cat, we won't go over. But hedgehog?
So in this case, right. So this is interesting, right? In this case, it depends on what you do. So do you have a value system that values cat over hedgehog? I can adapt my question to my answer to that. So
yes.
Yeah. Okay. Which one is it?
There's a lot of flat hedgehogs around.
Which is interesting, because it relates back to this conversation where we say we all have value systems. So I might not necessarily agree with yours, or yours, or we might not agree with each other with the detail of what it is, but we all have them. Right? Which goes back to the trolley problem, where somebody then says, well, is it the granny or is it the bus full of students? Same idea.
Do your autonomous vehicles observe speed limits?
Yes.
How do they observe the speed limits?
Because they know where they are. And we know
Are they looking at signs or picking up from GPS? Or?
They actually, so we don't use GPS, but we know where we are through the localization system.
So you've seen the signs and it's been recorded?
Both. So they know where they are, and so just like we annotate traffic lights, we annotate where the speed limits are in those places, and we also look for.
So they never go above 70 on a motorway?
No.
Well done.
What happens when you meet up?
You know,
to bring a green car. That's fine. What does it, to avoid your original winning system, it realises it can't pull up fast enough because car and bus stop suddenly. It doesn't give it the remit to say, branch out of that channel and say, I am trying to avoid every possible at whatever cost.
Not at whatever cost.
Okay, well when this, I mean, in that example, if it couldn't pull up in time, will it branch out of that channel that it's usually following?
So, okay, here's a really important bit. Don't think of it as a channel. Think of it as a guide. Okay? And this is really important. So when I said at the time, we don't hook this up to the steering wheel and the accelerator, that's exactly what I mean, because there's some people out there that do that. Okay? Or work towards being able to do that. So, do you remember what I just said about this notion of having this cost function? Right? So there's some cost function that is super hard. It says my low-level system says there's stuff, don't hit it, super expensive, this must net out. Okay? And then there are other factors that factor into this general cost landscape, like for example the system that I've showed you, that says, and if possible, it'd be nice to generally drive along this particular route. And so when something like that happens and something like somebody pulls out, the low-level systems tend to then pick up and go, actually there's something here, we need to find a better plan quickly. Right? And that is then what happens. So in this case, it would actually...
It would try to avoid and go to the blue channel, but not to the point of going
to red. As long as it's safe in the sense that it doesn't hit stuff.
Yes, it doesn't stop that.
Related to the question about speed limits, what would happen on the motorway where you've got dynamic speed limits? Is it able to read the signs? Is it able to follow lane discipline? Navigate roadworks?
Many questions.
Yes.
Potholes is a great example actually. There's some really interesting stuff about infrastructure management to be done. So managing the roads and the infrastructure in the country is a really big piece of work, and this technology will be central to that. Have a conversation to one way. Back to your question. Sorry.
In general about driver awareness.
Yeah. But not just about that. It's what was about recording. But back to your question, which I kind of almost forgot, dynamic speed limits. So the answer is we haven't really tried that, so I don't know, as far as I'm aware. But there are a couple of things there. One is the notion of, again, reading the road infrastructure, so the road furniture, so reading those signs, one thing. The other thing is the smart motorway sort of sense doing the two-vehicle communication, that's another thing. And of course, and roadworks is particularly bad. Roadworks, really hard. I find sometimes they're very tricky. I just went north to the Lake District where there's like only 6 of the most ridiculous roadworks twice. And I find it difficult to drive on because actually the markings themselves are very confusing. Right? And I wouldn't go anywhere near saying that's solved. I think that's a really tricky bit. Yes, sure.
How would you deal with external accidents in terms of the vehicle?
Sorry, how do we deal with
an accident external to the vehicle? So, for example, a lorry turns over in front of you on a road using that down, you've got to take a decoy. Do you have a remote control system driver from somewhere else can actually take over the vehicle remote?
I have a guy sitting in the car taking over.
Yeah, and I'm thinking when you first put this on with no person there, so the vehicle's going to turn.
That is a really good question. So again, this is somewhat in the future, and I can imagine a number of ways this would work. So for example, when something bad happens to traffic, both my phone and my sat nav know about it. So I can in fact my sat nav will reroute me, right, based on that. And so that information is already coming into the vehicle, and we can absolutely integrate that with the route plan. Because below everything, when we talk about, does it know how to avoid stuff, which is sort of a local plan, very local to where you are. There's also the high-level route plan that says, actually, I'd like to get through to Kimber. Right? And so that feeds into it.
We're coming up for 9 o'clock, so we need probably just one. I think you've been raising maybe just a couple of questions. I'm really sorry, but we need to be out by 9. So, gentlemen.
All your footage is forward-facing cameras. To what extent is this where everything's behind and beside you?
I'm just showing you this because it's the thing that people tend to most relate to. It has 360-degree view in all modalities.
Do you deal with sound or anything like that? Because when you're driving, you listen to the road, listen to what your car's doing. ambulances, that sort of stuff. So do you do anything like mapping sounds to certain what you need to do?
So that's an excellent question, because I think that's a largely overlooked sort of thing. The answer is on the research front, absolutely, that's something that's coming. So yes, even though it's not yet in the deployment systems, but it's an obviously really good. But that, I mean, great, really good point.
Okay. I'm sorry for anybody that's still got questions. There are loads there, but perhaps we could just thank Ingmar. Thanks very much, everybody. Hope to see you at our next talk.